Kia koutou katoa, welcome back to another exciting AP Chemistry video. Our focus today is going to be on the concept of chemical equilibrium. So what we're going to learn in this particular part of the unit is that not all reactions go to completion. In most reactions, you're going to have some amount of products and some amount of reactants at the end of your experiment. As a result of that, we are going to find a variety of different ways to calculate how much product we get in a reaction. Furthermore, later on in the unit, we are going to learn how we can alter that chemical reaction to shift to make more product or less product, and understand how to calculate concentrations at equilibrium. So I'm super excited for this video. Let's go ahead and get started. So we have quite a bit of learning objectives for this very first video, but in this first video, it's going to be very simple. We just need to understand some concepts about what is happening at equilibrium, understand the meaning of the value for K, understand the meaning of the value for Q, and understand how to manipulate values of K for smaller parts of a chemical reaction. Let's get started. So many of the reactions that we take a look at on a daily basis, we've drawn with a single arrow, but the reality is that they can go both ways. Many reactions are reversible. I mean, even think about the concept of evaporation and condensation. To make the reaction go the opposite direction, we just need to alter the temperature or the pressure at which the chemical reaction is taking place, and we can get evaporation or we can get condensation. So not all reactions go to completion. In fact, very few of them do. So we use this term equilibrium, and it occurs when there is no change in the system. Now, that does not mean that the reactions are not taking place. It is dynamic. And when I refer to dynamic equilibrium, it simply means that the rate of the forward reaction is the same as the rate of the reverse reaction. So it appears that no reaction is taking place because I'm making products at the same rate at which I'm making my reactants. Thus, it looks like it's exactly the same. So we are simply at equilibrium when there is no change in the system. But again, remember that it is dynamic. The rate of the reaction in the forward direction is the same as the rate in the reverse direction. So that's why it appears that no new product or no new reactant are being formed. So graphs are really nice because they can show the relationship between the forward rate and the reverse rate of the reactions, as well as the amount of product or reactant that is given. If the forward rate of the reaction is greater than that of the reverse rate, you're going to make more products. Makes sense. If I've got more going forward and less going backwards, then I'm going to make more product. If the reverse is true, and the reverse reaction is greater, more reactants are produced. So these two graphs are really important because they show rate as well as they show amount. Now the rate of the forward reaction starts off very high. We're assuming we just have reactants here and no products, and it makes sense that the forward rate is quite high and the reverse rate is low. You can't start a reverse reaction until you have some products in your chemical reaction. But over time, what happens is that those rates become equal. Now if we look on the right-hand side here, notice that the amount of reactant and product is not equal. However, the amount of reactant and product does not change. Thus, what we say is that the system is in equilibrium because the rates going forward and reverse are the same, and there's no change in the amounts at equilibrium because the forward and reverse rates are the same. So with this information, we can calculate some very special and important values. We need to know the relative exponents and the concentrations or pressure. We can write out what's called the reaction quotient, which is a value given for any time in a chemical reaction, or an equilibrium expression, where something is at equilibrium. It is simply the pressure or concentration of your products over the pressure or concentration of your reactants. One thing to remember here is that we are going to take our coefficient, and our coefficient becomes our exponent. Now, I talk a little bit about Q and K, and we don't really have a whole lot of context for that. But Q can be calculated at any time during a chemical reaction. You can calculate at the very beginning, you can calculate it at the end, you can calculate it at equilibrium. K is specifically for when a reaction is at equilibrium. And what's nice is that we can compare the values of Q and K in order to determine which direction the reaction is going to proceed in order to reach equilibrium. So at equilibrium, Q is going to equal K. Sometimes you may see variables like Kc, which is just an equilibrium constant for concentration, or Kp for partial pressures. You can convert those two variables into one another. We won't have to worry about that in this class. And do remember that when we are finding equilibrium values, we do not have any solids or liquids. They do not have a concentration, nor do they exert a partial pressure. So we don't include solids or liquids in our equilibrium expressions. So let's talk about the difference between Q and K. And we need to understand some really important values for Q. Some really important values for K. If K is greater than 1, more products will be present at equilibrium. Now think about that. If K is greater than 1, then what is in my numerator must be larger than what's in my denominator. Well, that makes sense that K would be greater than 1 because the number on top is greater than the number on the bottom, and it's products over reactants. And it's the same for when the value for K is less than 1. It refers to the fact that we are going to have more reactants present at equilibrium. And again, that makes sense because if the numerator is smaller than the denominator, then K is going to be less than 1, and in the denominator, hard word to say, in the denominator, we have more reactants as opposed to products. Now, when we're comparing Q and K, what I like to say is when you're comparing them to follow the alligator mouth. So when Q is greater than K, we're going to make more reactants. So Q is to the left, so I just think of it as the reactant side, even though it's not solely applicable here. But when Q is greater than K, our reaction is going to shift to make more reactants until equilibrium is reached. When Q is less than K, we're going to make more products. That is, the reaction is going to shift to the right, and we're going to make more products until equilibrium is reached. Remember that Q does equal K at equilibrium. So lots of things to remember here, but just remember the concept of K being greater than 1, we have more products at equilibrium. K being less than 1, we have more reactants. If Q is greater than K, then we're going to make more reactants to reach equilibrium. And if Q is less than K, we're going to make more products to reach equilibrium. So the reaction quotient or equilibrium constant can be calculated if concentrations or pressures are known along with a balanced chemical equation. So for example here, I have a nicely balanced chemical equation and I want to know the value for K when we have 1.60 atm of H2O and 0.030 atm of CO and H2. Well, the first thing we're going to do is write out our equilibrium expression. We're using partial pressures here, so I typically use the P to represent the pressure of each individual component in the chemical reaction. Notice that I did not include carbon because carbon is a solid and we do not include solids or liquids in our equilibrium expressions. Now all I simply do is I just plug in all of my variables and solve. And K gives us a value of 5.63 times 10 to the negative fourth at equilibrium, which means that I have more reactants than products at equilibrium. And we can see that based on the value of the partial pressures. 1.60 atm of H2O implies that there is significantly more H2O than something that exerts 0.030 atm of pressure. So you can always check your K value with your amounts in molarity or your amounts in pressure to check to make sure that it works. So let's talk a little bit about the equilibrium constant. The size of the equilibrium constant itself is directly correlated to the amount of products or reactants at equilibrium. So consider it to be a continuum. If I have a very, very large value for K, then that indicates that a reaction almost goes to completion. A very, very small value for K indicates that the reaction yields almost no product. And then those somewhere in between, a value of 10, let's say, you're going to have some reactant, some product. With the K value of 1, you have the same amount of reactant and product. So the value for K itself is almost like on a meter per se. The much larger values for K means that the reaction goes essentially to completion. Very small values for K indicate that almost no reaction takes place at all. Now, we can manipulate the value for K. Think back to Hess's law, where we combined a bunch of smaller chemical reactions in order to get the delta H of the reaction for a much larger chemical equation. Well, we can do the same thing for the values for K. We need to make sure that we understand the ability to manipulate those values for K as well. So for example, remember in Hess's law when we multiplied the reaction by a coefficient, so in order to get instead of H2, we get 2H2. Remember that when we multiplied that, we multiplied delta H. Well, in this case, because we're dealing with exponents, the value for K is raised to the power of whatever coefficient you add. Reversing a reaction inverts the value for K. So instead of it being K, it's 1 over K. Remember with Hess's law, we just flip the sign, but in this case, we need to flip our reactant and product. Remember that it's in a fraction, so we have to do that. Now we can combine multiple reactions together in order to get the value for K for a much larger chemical reaction or a reaction that we just simply don't have the value for K for. But remember with Hess's law, we added them up. Well, with the values for K, we are going to multiply them. So I always think of Hess's law when I do this. I just think that the equilibrium, we just take it one step further. So instead of flipping a sign, we're going to do 1 over the value, or instead of multiplying it, we're taking it to the power, or instead of adding them at the very end, we're multiplying them out. So let's take a look at an example here. I want to calculate the value for Kc for this reaction, and I'm given the following, and I need to be able to manipulate this in order to get this to work. Well, the first thing I'm noticing here is that we need 2 N2O on the left side, so I'm actually going to flip that very first one. So that way it is on the left side, that 2 N2O. The next thing I'm going to do is I'm actually going to flip the second one, okay, because I need 2 N2O4 on my product side. So I'm going to flip it and then I'm going to multiply it by 2. And then for that very last one, I'm going to keep it as is. And so that very last one, I'm actually going to keep it as is, but I'm going to multiply it by 4. And that's what's going to give me everything I need in order to cancel out, in order to give us our equation at the very top. Okay, so again, think just like Hess's law. We can manipulate the value for k by utilizing the rules that we just discussed on the left-hand side. So the very next step in this is thinking about what we have to do for the value for k. So in this instance, we flip the first one. So instead of 1.2 times 10 to the negative 35th, we're going to do 1 over 1.2 times 10 to the negative 35th. For the second one, we flipped it and squared it. So in that case, we need to go 1 over the value for k for that reaction, and then we're going to square that value in the denominator. And the very last one we raised to the 4th power, so we need to take the kc there and raise it to the 4th power. So, and then what we do when we're done is we're going to multiply all those values for k together, and what we get is 1.1 times 10 to the 6th value for k, which means that it strongly favors our product production as opposed to our reactant production. This is a great way to take, again, smaller chemical equations and figure out how we can make a reaction where we get most of our product being made. So we covered quite a bit of student learning objectives. Not a lot of practice problems, but we will dive more into that as we get into class. I just want to make sure that you understand kind of some of the basic concepts that we are covering moving forward. So as always, if you have any questions, make sure that you let me know. Make sure you like, comment, subscribe. Have a great day, and we'll see you soon. Bye-bye.